Hello. In previous videos, we've analysed homogeneous systems of differential equations, particularly linear systems of ordinary differential equations. In this particular example, we have a non-homogeneous system of two linear ordinary differential equations. In equation 1 and 2, as you will see. I formed them into this, or I've at least put them into this matrix form, which we call equation 3. And we're going to proceed to solve this in a similar way to how we would solve non-homogeneous ordinary differential equations on their own. So just to give you an example, if we had x dot minus 3, x double dot 3x dot plus 6x equals to e to the minus t, you would first solve this part of the equation by putting the left hand side x double dot minus 3x dot plus 6x equal to 0 and solving as normal to find a complementary solution that would give you x in terms of time t. And then what you would do for the particular function would be to substitute x equals a e to the minus t. And then substitute that and its two derivatives, both the first derivative and the second derivative, into that equation, equate it to the right hand side and solve for the constant a. That is essentially what we're going to do in this particular case here. It's exactly the same sort of thing, except that this analogy for this system is written with everything on the right hand side brought over to the left. So this could be rewritten as x double dot equal to 3x dot minus 6x. And again, you can solve that by forming it into that type of equation and then solving. So what we're going to do is we're going to make a start with equation 3. Now, as with our previous videos, we're going to let a equals 6, 4, and 1, 3. So this part of the matrix here, and that is multiplied by the vector x, y. Now, for the eigenvalues, we find lambda I minus a, or the determinant of it. The determinant of lambda I minus a, which is simply equal to lambda minus 6 minus 1 minus 4 there, lambda minus 3. And that's got to be equal to 0 because we want linear combinations of the final equations, which I think I might have explained in a previous video. Fortunately, the determinant of matrix A is not equal to 0. That indicates that these row entries are not multiples of each other. If they had been, that determinant would have been equal to 0, and it would have complicated things, if not made the problem insoluble. So anyway, this determinant should not be equal to 0 in this case, we want the determinant to be equal to 0, so that we can then find the appropriate eigenvalues and eigenvectors. And of course, finding the determinant of this part of the matrix, we get lambda minus 6 times lambda minus 3 minus a minus 1 times a minus 4. And that's got to be equal to 0. So if we just multiply this out and simplify it, we obtain lambda squared minus 9 lambda plus 14 equal to 0. Now, fortunately, this equation can be easily factorised. And so we've got lambda there and lambda there. Two numbers which, when multiplied together, give plus 14 are 7 and 2. Plus 7 and plus 2, or minus 7 and minus 2. But which? Well, we want those two numbers which, when added together, give minus 9. So this must be minus 7 and this must be minus 2. Minus 7 minus 2 is minus 9. Minus 7 times minus 2 is plus 14. So the e-values, or the eigenvalues, well, actually, I'm jumping a step there, aren't I? Because we should be writing, therefore, lambda minus 7 equals 0, or lambda minus 2 equals 0. That leads to the eigenvalues of lambda 1 equals 7, or lambda 2 equals 2. Right, so consider lambda 1 equals 7. So when lambda is equal to 7, this matrix can be written as, we'll call it B1. Well, I'll do this without writing it down to conserve space. 7 minus 6 is just 1. Then we've got minus 1 here. We've got minus 4, that just stays the same. And we've got 7 minus 3, which is 4. And that's multiplied by the vector xy, and that's equal to 0. Now, hopefully you can see that these equations, 1 and minus 1, and minus 4 and 4, are just multiples of each other. And so we get the form x minus y equals 0. So that times x gives x, I'll say it again, 1 times x is x, minus 1 times x is minus y. So we can choose x to be equal to 1 and y to be equal to 1, because when we substitute 1 in for x, making mistakes again. When we substitute 1 in for x and 1 in for y, we get 1 minus 1, which is 0. So because x and y, x equals 1 and y equals 1, results in that equation being equal to 0, we know we have two components of our first eigenvector v1, which is c1, 1 and 1. When lambda is equal to 2, we have B2 equal to, well, when we substitute 2 in for here, we get 2 minus 6, which is minus 4. Then we've got a minus 1 here. That stays the same. That minus 4 stays the same. And we've got 2 minus 3, which is minus 1. X, Y. So this implies that, well, we can see that the equation in row 1 is exactly the same as the equation in row 2. So therefore, they're essentially both one and the same equation. They're multiples of each other. And we can simplify them to give 4x plus y equals 0. This implies further that x can be chosen to be minus 1 and y can be chosen to be 4. And as you can see, when you've got x equal to minus 1, you've got a minus 4 here, plus 4 equals 0. So that is our second eigenvector. Okay. So V2 equals C2 times minus 1 and 4. So a complementary function is x equals x, y for the vector equal to C1 times 1, 1 times the exponential. Well, the eigenvalue associated with this eigenvector is 7. So it's 70 plus C2 times minus 1 and 4 times the exponential. We know that the eigenvalue associated with this eigenvector is lambda equals 2. So that's just 2t. Now, we're not finished because we now have to consider a particular function. So let the particular function xp be equal to, well, we know that's 6t and that's minus 10t, but we don't know what the actual entries of the particular function will be. So we'll just call that A1 and B1 times t plus, and we don't know what the constant in the end is going to be for the actual solution. We can see what these values are here, but this isn't the actual solution. It's just the series. It's just it's just a system of two equations, two linear ordinary differential equations. So we'll call one of our constants A2 and the other constant B2. Right? So, like I said, in the case of a second ordinary differential equation, you have to substitute the particular function for x and all its derivatives, right? So we can see that x dot p, not forgetting that xp is little xp, yp as a vector, and so x dot p would be x dot p, y dot p there. and that's equal to that. And if you differentiate everything on the right hand side of that equal sign, then the t disappears, leaving you with a1, b1. And the a2, b2 vector disappears altogether. Any constant which, when differentiated, always equals 0. So we can now substitute this and this back into this equation. So we get A1, B1 on the left-hand side, and that's equal to 6, 1, 4, 3 times, in brackets, and this is our xy vector, which is this here. So I'm just going to multiply all the entries out by t there and add them to the constants here in this matrix up here. So we've got A1t plus A2 and B1t plus B2. So we've substituted that in for x, y vector there, and there's something else we have to add on. We also have to add on this bit. So we've got plus 6t plus 0 and minus 10t plus 4. So let me see if I am getting the right, okay, so when you multiply everything out and simplify it, we've got A1, B1 on the left-hand side, and that is equal to, and I'm going to simplify this, but hopefully by doing the right matrix multiplication, you'll be able to see what is happening here. But you multiply these entries by everything in this column matrix here. So 6 times all of this plus 1 times all of this plus 6t plus 0, and then 4 times A1t plus 3 times, 4 times A1t plus 4A2 plus 3B1t plus 3B2. I hope I've said all that right, but if you follow through, it should be okay. So multiplying out, we get 6A1 plus B1 plus 6 times t. So there you are, 6 times A1t plus 1 times B1t there. Actually, you could have multiplied by the 6 by everything there, and so on like that, but you would have had to separate it all out. So underneath we have 4A2 plus 3B2 minus 10t. And then over here we've got plus 6A2 plus B2, and underneath we have 4a2 plus 3b2 plus 4. So basically, multiplying everything out in those brackets and then writing what you get like this, then you can solve two sets of simultaneous equations. So we have 6a1 plus b1 plus 6 equal to 0, and 4a1 and 3b2 minus 10 equals 0. Solving, and I'm not going to solve these because hopefully you should be able to do it yourself. We get A1 equals minus 2 and B1 equals 6. And by the way, that should be B1. I think I've made a mistake there. Yes, that should be B1. Now, we also get another equation, 6a2 plus b1 equals 0. Excuse me. And 4a2 plus 3b2 plus 4 equals 0. So that's this bit up here. They all have to be equal to 0. So solving, we find that A2 is equal to minus 4 over 7 and B2 is equal to 10 over 7. So we can write down the general solution. Right, there we are. So, a general solution is x equals, we'll put our vector in of xy, and that's equal to C1, 1, 1, e to the 7t, plus C2 times the vector minus 1 and 4, e to the 2t. Well, if you remember, our particular function was xp equals a1 b1 t plus a2 b2. So if you just substitute these values for a1 and b1 and a2 and b2 into this, then you get I'll write it over here. A1 is minus 2 and B1 is 6 times t plus, in brackets, minus 4 over 7 and 10 over 7. You can take out the 7 if you wish, so that you've got x vector x is equal to c1 1 1 e to the 7t plus c2 minus 1 4 e to the 2t plus minus 2 6 t plus 1 over 7 times minus 4 and 10. And that is the general solution. In analysis of what I've just done, I don't think I really explained what I was doing up here as clearly as I should have done, but I hope it's self-evident what you have to do to solve this equation. You have to equate this to be 0 and this to be 0 and then solve for A1 and B1, and you also have to solve this equal to 0 and this part equal to 0 and solve for A2 and B2, because for this to work all of that side has to be equal to 0. And then once you've found A1 and B1 and A2 and B2, then you could just substitute into the particular solution form or the approximate form of the particular solution and add it to the complementary function, and then you will have your general solution, which is that. So hopefully that's been okay for you, and you will come back and watch previous videos and also watch any future videos that I upload. And so it remains for me to say, well, I bid you farewell for now, and take care and goodbye, and see you next time.